Today's frontier AI models possess incredible raw reasoning capabilities. Give them a complex logic puzzle or ask them to write an application from scratch, and they generally nail the task. But there is a massive blind spot. These models are frozen in time at their training cutoff date. They have zero visibility into your proprietary codebases, internal wikis, or real-time support databases. When an AI lacks specific information about your business, it compensates using its base training. You end up with outputs that are beautifully formatted and confidently delivered, but factually wrong or totally generic. Scaling AI beyond generic chat requires context engineering, the specific infrastructure needed to deliver the right data to the model at the right time. At the infrastructure level, you have to decide exactly how you will inject this missing data into the model. Right now, architects are split between two different philosophies. The first approach is long context. This is the brute force method of simply dumping raw, massive files directly into the AI's prompt window. The second approach is Retrieval Augmented Generation, or RAG. This is an engineering method where you build a pipeline to search your data, filter out the noise, and deliver only specific, highly relevant snippets to the AI. For years, context windows were tiny, making RAG your only viable option. But with modern models handling over 1 million tokens, enough to hold an entire fantasy novel series at once, the boundary between these two choices has blurred. This architectural choice dictates how you manage compute costs and retrieval accuracy as your data scales. We'll start with long context, which offers a major advantage for developers who need to move fast: absolute simplicity. It gives you a no-stack stack that removes the need for databases and embedding models. This diagram illustrates the whole book problem. If you ask an AI to compare the original product requirements with the final release notes to see which security features were omitted, traditional search tools struggle to retrieve the gaps between them. Long context allows the AI to holistically compare both full documents simultaneously, enabling the model to spot the missing pieces itself. That holistic reasoning comes at a steep price. If you drop a 500-page manual into the prompt window, the model has to process all 250,000 tokens every single time a user asks a new question, creating a severe compute inefficiency. Throwing that much data at the model also causes the needle in a haystack problem. An artificially massive context window dilutes the AI's attention. If the specific fact you need is buried on page 300, the AI might miss it completely, or hallucinate details based on the surrounding noise. Long context trades computational efficiency and pinpoint accuracy for unmatched setup simplicity and holistic document reasoning. When you step into the enterprise world, you aren't dealing with a few manuals. You are dealing with data lakes measured in terabytes. Throwing the whole book at the AI becomes mathematically impossible. Here, we see the mechanics of basic RAG. First, your massive source documents are broken down into smaller, uniform chunks of text. Those chunks are converted into vectors, long arrays of numbers representing their meaning, and stored in a specialized database. When a user asks a question, the system performs a semantic search. It filters out the noise to select only the top 3 most relevant vector blocks and sends those directly to the AI. The primary vulnerability of this system is the retrieval lottery. Semantic math is probabilistic. If the search step fails to find the exact matching vector, the AI never receives the data, resulting in a silent failure. Basic RAG guarantees low inference costs and high signal-to-noise ratios, but it relies on the assumption that your database search logic is flawless. Because basic semantic search can fail on complex queries, enterprises must evolve beyond simple retrieval pipelines to true context engineering. This diagram shows graph RAG in action. It uses a knowledge layer to map entities and hierarchies, explicitly linking a specific client to their support tickets, contracts, and personnel. Graph RAG traces these specific structural pathways to pull highly precise, interconnected context that a basic vector database would easily miss. But precision retrieval alone isn't enough for a production environment. The final pillar of enterprise AI is runtime governance. A context system must verify user permissions in real time. If an employee asks for a meeting prep document, the system has to actively block the AI from ingesting or outputting restricted data, like internal pricing discussions, that the specific user isn't authorized to see. By mapping specific data relationships and enforcing permissions at runtime, you create a memory architecture that is both structurally reliable and audit-ready. The goal of a modern AI architecture is precision, delivering the leanest possible set of facts required to complete the task. The architectural choice starts with the scale of your dataset. For bounded datasets requiring holistic reasoning across entire documents, long context wins, trading compute costs for rapid developer speed. But for infinite, changing data lakes requiring specific lookups and permissions, RAG is mandatory. A massive token window can hold millions of words, but it can never serve as a replacement for a secure, permission-based enterprise data warehouse. Look past the hype of million token models. Assess your data's constraints and build the memory architecture that specifically filters your noise.